So most commonly encountered flow geometries: a flat plate, flow over a cylinder, flow over a sphere, and you have a tube banks. So these are the 4 common geometries that we are going to cover in this chapter. So let's start with the flat plate. So flat plate is, in terms of, equation, it's the simplest one to analyze, but it's fairly complicated. So as we mentioned in chapter 6, you need to write down coupled partial differential equations. Mass, momentum, energy balance has to be coupled, and these are partial differential equations. And so you can obtain some sort of an approximate solution by using the following assumptions. So if we assume the flow is steady, incompressible, laminar, properties are constant, and pressure gradient is 0, then so we will have somehow somehow easier to obtain a solution. So now let's take a look at the development of boundary layer here. So if we send a fluid that is at velocity u infinity over a flat plate, so initially you'll have a laminar boundary layer, and then it's going to transition into transition region, and finally you'll have a turbulent layer. So, and the thickness of this boundary layer, we will be using thickness is delta. So that is how we are going to denote. And the distance at which the transition happens from laminar to turbulent flow, we call it x critical. So that is the distance at which. And if you want to calculate the Reynolds number at any length L, so we just use that length to calculate the corresponding Reynolds number at that particular L. So if the Reynolds number is smaller than a critical Reynolds number, we have laminar flow. And if the Reynolds number, so the critical Reynolds number is 5 times 10 to the 5. Okay, so that's the idea here. So also you would like to pay attention to the direction of the flow. Flow here is mostly in X direction. In transition and turbulent region, we have significant flow in Y direction. Okay, so this is important to realize. So again, so we just made some assumptions, and we talk about visually how the flow behavior changes from laminar to turbulent flow. Now let's take a look at the equations. Again, we are not going to go through full solution of the equations, but I'll just show you the ideas behind the boundary layer analysis of a flow over a flat plate and corresponding heat transfer. So we have a flat plate. So the velocity, there is no flow. The liquid molecules on top of the plate will stick. So this is no slip boundary condition. And then in the velocity in this direction, this is velocity in X direction, this is velocity in Y direction. So velocity in Y direction is also 0 here. The molecules are stuck, they will not move when Y is equal to 0. And temperature at the surface is Ts. So these are the boundary conditions. And we have continuity equation, Navier-Stokes equations, and energy balance. And then solution of these differential equations, the coupled differential equations, can be obtained by using the similarity approach that we discuss when analyzing the semi-infinite objects. So this is the equation here. So this is eta, similarity variable, and it's a function of bulk velocity, kinematic viscosity, and again this is a constant. Kinematic viscosity and constant. X is the variable here, and Y is also a variable here. Okay, so and then this could be solved by using the stream functions. Again, this is going back to fluid dynamics. So the definitions of the stream function in Cartesian coordinates. So continuity equation can be written in terms of the stream functions as shown in here. Okay. So again, this the similarity variable here is slightly different from what we talk about in terms of the form, but the only difference is basically the constants. The variables y over square root of x is similar to x over square root of t. So the form factor of the equations is the same. So again, after you go through this analysis, so I'm not going to spend time on actually solving these partial differential equations using the similarity variables, but you should know that the boundary layer for a laminar flow over a flat plate can be solved analytically using the similarity approach. It is still lengthy, and I'm going to just show you the final results. I'm not going to go through the derivation. So the thickness of the boundary layer is basically equal to 5 times x over square root of Reynolds number. So if we have a flat plate, and let's say if this distance is x, so if you want to calculate the thickness delta here, so we need to write down the x value, and we need to calculate the Reynolds number for this x distance and take the square root of that, and that's going to give us the thickness of the boundary layer. And if you want to calculate the drag coefficient at a particular point x, so we have the Reynolds number, and we take Reynolds number to the -1/2 power and multiply it by this constant, and we obtain the local friction coefficient. Okay. So these are the hydrodynamic properties. These are important because sometimes there are some equations for estimating convective heat transfer coefficients in terms of these variables. In chapter 6 we learn about Colburn correlations, and in that case this the local friction coefficient was allowing us to calculate convective heat transfer coefficient. So how about the thickness of the boundary layer, thickness of the hydrodynamic boundary layer? So the correlation is simple. So the thickness of the ratio of the thickness after you calculate delta, this is hydrodynamic thickness. And so if you want to calculate the thickness of the thermal boundary layer, so they don't necessarily have to be the same. So the ratio of these two is equal to Prandtl number to the 1/3. So if the Prandtl number is 1, the thickness of the thermal boundary layer and hydrodynamic boundary layer is the same. But if it is not 1, so we have this equation that will allow us to calculate the thermal boundary layer. So a thermal boundary layer is simply delta times PR to the -1/3, and we have the expression for delta. This is for hydrodynamic one. This is how we calculate the thickness of the boundary layer, thermal boundary layer. And for the local Nusselt number, so Nusselt number here, so we have a plate, and in this case this distance is x, and if you like to calculate what is let's say this is going further, what is the local convective heat transfer coefficient? H is local and H bar is average. So what is the local value at this particular x? So it is a function of Reynolds number for this range and Prandtl number. And again, the definitions, we already talked about the definitions of this dimensionless number earlier. So you know x, you know the fluid thermal conductivity, and then you can simply calculate Hx from this empirical equation. So if we are interested in average properties, so again, if we have, let's say, if you want to obtain an average property for this section X, so if we are averaging all the friction coefficients across this length X, So this is the expression here. So Reynolds number evaluated at x to the minus 1/2 multiplied by 1.3. That's going to give us average friction coefficient along this across this length x. And we can also calculate average Nusselt number. So again, h bar or Nusselt number bar indicates this average. It's not at this point, it is for a whole system. And in most of the macroscopic analysis, we use the average property. And again, as I mentioned earlier, in chapter 1 through 5, we have been always using the average, although we didn't distinguish between average and local properties. So it should be important to remember, average, chapter 1 through 5, we always use average. And now, if you want to calculate the average for a particular size or particular length, we will be using this equation. Again, this is here the average convective transfer coefficient, and it's a function of Prandtl number and Reynolds number. So the next question is all of these properties. So for instance, if I want to calculate Reynolds number, I need to know viscosity, I need to know density. For Prandtl number, I need Cp, I need K fluid. So the question is, if there is a, let's say, there is an object, let's say at Ts, and we send the fluid around it at T infinity, so the temperature is going to vary within the boundary layer, right? It's going to change from Ts to 99% of T infinity. So there is a variation in temperature. So the question is, what temperature do you need to evaluate the properties? So you need to evaluate Reynolds number. So you need to know what viscosity should you use. And if you take a look at this graph, the viscosity is a very strong function of, this is basically kinematic viscosity is a strong function of temperature. So density is a weak function, it is linearly changing, but this is an exponential decay. So the kinematic viscosity is strongly changing with temperature. So the question is, at what temperature do you need to evaluate these properties? Ts or T infinity? Or a combination of these. So, and heat capacity also a weak function of temperature, but in general they behave mostly linear in short temperature ranges. And thermal conductivity is also a weak function of temperature. So in most of the equations, we will be using a temperature called film temperature. Film temperature means it's average of surface temperature and bulk temperature. So we will be evaluating the properties, evaluate properties at this temperature, unless otherwise stated, okay? So we'll be seeing many different empirical equations. Most of them for external flow will depend on film temperature. So the evaluation has to be done at T film.